So numbering systems is code. We're going to explain the decimal numbering system. I'll teach it hopefully the way it actually is. Sometimes they don't teach it. Scientific notation, exponents, explain integer numbers, fractional numbers, and real numbers. Describe the binary number system. Convert decimal numbers to binary and vice versa. Perform some binary math. I'm not going to spend much time in that. Explain the hexadecimal numbering system, convert binary numbers to hexadecimal, explain the octal number system, convert numbers between octal, vice versa, explain the binary coded decimal system, and we're going to look at BCD, which is binary coded decimal. We'll look at gray code, ASCII, Hexadecimal, and something called Unicode, which I don't know if the guys put this in this book yet or not. These are codes. Are we okay? So, first of all, an exponent is a number written above and to the right of another number base that indicates the number of times the base is to be multiplied by itself. So if I said a to the fifth, then what that actually means, that means we take a and multiply it by itself what? 5 times, which comes up and gives me 32,768. Everybody okay there? Any questions there? Y'all seen this before, right? Everybody okay? Most calculators have the ability to do this. They either call it y to the x or x to the y. And what we have the ability to do, wrong computer. What we have the ability to do is, let me get to this desktop, which is this guy right here. Oops. So this computer calls it x to the y. I don't know, different computers call it y to the x. So if you're going to use this key on your calculator, you hit the base. So the number that we're raising the exponent to is called base, right? Everybody okay? So I enter the base, and I enter y to the x, and then I enter what I want to raise it to, and I say equals, and it comes up and gives me the number. And just about every calculator, it's either called y to the x, or it's called x to the y. It depends on the calculator. Everybody okay? And this is the world famous Windows calculator. Scientific notation, this is a way that scientists and engineers use to handle very large and very small numbers. It's written in the form of x times 10 raised to some power. Everybody understand that? So what we would do, instead of writing this number, is I would come up here and I'd grab the decimal point and I'd start moving it. Now what we're looking for is we're trying to get this decimal point up till we get to our first whole number, or first whole number, right? So I come over, I go what? 1, 2, 3, 4, 5, 6, 7. And then I would write this as 5.6 times 10 raised to the 7th power. Okay. Minus 7th power. If you go to the left, it's plus powers. If you go to the right, it's minus powers. Okay? I should have said that right there. Over here, we'll move it over, and what we're shooting for on this is trying to get one whole number. Does that make sense? So I come over, I go 1, 2, 3, 4, 5, right? Understand that? And then I write this as 1.57 times 10. Are you okay? Any questions there? Y'all seen this before, right? Everybody seen this before? We okay? Yes? Rounding. This gives people problems all the time. What we're doing is we're looking at the number depending on how far we're going to go. So here we're looking at rounding to 2 decimal points. Okay. So what I do is I would come over here. This is where my decimal point over here. I'll start moving it. It's a whole number. This is not the sign of the number. This is what PowerPoint puts in there. 1, 2, 3, 4, 5, 6, 7, 8. Are you okay? So I'm gonna come down here, I'm gonna start writing 1.05. Now, why is this a 5? Well, we carried it out to 2 decimal points. So what we'll do is we'll look at this number right here. Everybody okay? But we also got to look at this number right here. So what would this number round this number to? 4. And then this number is below 5, right? You understand? So we will leave it off. Everybody okay? Makes sense? Whole numbers move to the left until only one number is left. If we're using scientific notation. Any questions so far? What we've done over time is the powers of 10 have gotten names. Now notice what happens. So I'll look this up on the internet. And it started off with, if I use, instead of using times 10 to the first, then let's write a number, which would be this one. Instead of saying, instead of saying 5.3 times 10 to the first, we would say 5.3 deca. And deca stands for times 10 to the first. Everybody okay? If I was going to say 5.3 times 10 squared, then I would use the term 5.3 deca. Everybody okay? Huh? Oh, I'm sorry. Yeah. This is first, this would be second, and I'd say what? Thank you. Now, over time, what has happened? Now, notice what above this, what they do is they start jumping in what? 3s. So what we do in engineer notation, which we'll look at, we don't have, well, we do have this one. You can't do away with 10 to the 0, but we do away with these 2 right here. Everybody okay? So what that means is if I was to come over here and have a very large number, what I would do is I'm going to start moving this, but I'm only going to move in groups of 3s. And I would go what? 1, 2, 3, 4, 5, 6. Everybody okay? Okay, everybody okay? Then I would say 1 point. Now this is depending on how far you're going to round. Let's round to 2 spots. So I'd say 3, 6. Everybody okay? And I moved how many times? 6 times. So I would use mega. Now normally we don't write mega out. This is the abbreviation we use for mega. So I'd say 1.36 here. Everybody okay? Now, what if I came up here and had this? I would go 1, 2, 3. Everybody understand that? But I've got to keep whole numbers. So this is where it varies with scientific notation and what we call engineer notation. I always got to keep whole numbers, right? Or I'm shooting for whole numbers. So here I would type in 11, and how many times did I move it? 3. So I would call this kilo, or I would call it a lowercase k. Supposed to be a lowercase k. Huh? Well, if we're rounding to 3 decimal points, I would say 11 point. Now, if I was going to write 356K, I've seen students do that. I might as well do what? Write the number. Y'all understand that? So let's round it or to 2 decimal points. So I'd say 11. I mean to 1 decimal point. I'd say 11 point what? Yeah, I'd say 11.4. Okay. Are you okay? Good point. Now over on the negative side, which means we're dealing with a fraction, right? I'm going kind of fast, but everybody okay? If you want to go back and look at this, we'll be fine. Some of y'all have already had this. So what I'm going to do here is, in engineering notation, we drop those, and the first one we have is what we call what? Milli, and we abbreviate that with a lowercase m, right? Now why do they use a lowercase? Because over here we use a what? Uppercase. And then we got micro. Well, we've already run out of m, so they use the Greek symbol for micro. Everybody okay? So I'd come up here and I'd start moving this. I'd say 1, 2, 3. Have I got whole numbers yet? Okay, so I'd go 1, 2, 3. Right? You understand that? And then I'd say what? Point. Let's just. 0.8. Yeah, 0.8. And then we would say micro. Everybody understand that? Are we okay? And it keeps going, but this is as far you'll go. This is where we're at in computers right now, up in the Tera. So we have a file server that belongs to our department, which is 6 terabytes. Not teras, like your grandkid. Right? Giga, y'all probably heard of Giga, right? Most people call it gigs. I hate that term. That's the commercial term they use. And then the meg, y'all probably familiar with meg. People call this meg. And then kilo. A lot of people just call this petty. And we don't deal in engineering notation. We don't deal with the other ones anyway. Everybody okay? So the difference between engineering notation and scientific notation is basically very simple. Is scientific notation defines those 3 down there, right? You understand? And what do we do in engineering notation? Engineering notation moves in groups of 3. And then you say how far you need to round it. But when we take our fraction, we're trying to get whole numbers. As soon as we get whole, or they're not actually whole numbers, as soon as we get the numbers on the left of the decimal point, I stop, right? You know what I'm saying? Right? And when we're in big numbers, we move it until we have numbers to the left of that. So engineers, we don't have fractions. You know, if you went out and you interviewed for a job and you call this 0.000399682, that guy's gonna look at you and say, you know, this guy has no idea what he's talking about. We interviewed for our jobs, our new instructor last, and they're not going to start this week. Hopefully they'll be on board next week if you're taking any classes. And one of the guys was giving this lecture, and he said a transformer steps power up or steps power down. No, transformer don't change power. Power in equals power out. What it does is change the what? Changes the voltage, which changes the current too. So as soon as he said power in, power out, I said this guy's got a problem. So the decimal number system, everybody okay with that? And it's 10 digits running from 0 through 9. And we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we're counting, when we run out, so if I was going to count, I'm going to go 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's all the combinations we have for one digit. If I want to keep counting, what am I going to have to do? I'm going to put a 1 out here, and I'm going to go to 0, right? You understand? And I'd go 10, 11, 12, 13, and I'd count all the way up until I got to 99. I've run out all my combinations. What would I do? I'd add a 0, I'd add a 1, put the other two digits to 0, and start all over, right? You understand that? So if you understand that, then this combination right here, we'll see that this is the same. We understand that combination right there. So how many times did I count? If I counted to 0. Right? I'm sorry, 1, 2, 3, 4, 5, I'm sorry, not from 0. 9, just to say what? 10, right? Each digit has a weight to the value of the number depending on its position. So if we came down here and wrote a big number, well, not a big number. What did y'all learn that was? Ones, yeah. Or okay, this is ones. What do y'all call this? Tens. And we call this hundreds. We call this thousands. And then we would call this 10,000. And that's the way you learned it, right? You understand? So if I wanted to find out how much weight this number had for the total number, I would take this and I would multiply that. So this holds the weight of 30,000, right? This holds the weight of what? 6,000. This holds the weight of 970 and 8. And if we add all the weights together, we would come up and get the original number. That'd be okay. Now, the way it actually goes, and we'll look at this, is that every numbering system, I don't care what it is, the way it actually goes is if we had that same number, what was it? 36,978. This holds the weight of the base raised to the 0 power. And any number raised to the 0 power is what? 1. This holds the weight of 10 to the first. This would be 10 to the second. This would be 10 to the third. This would be 10 to the fourth. The next one would be what? 10 to the fifth, 10 to the sixth, 10 to the seventh. Now I'm going to come over and put this guy right here, which is technically the radix point, but usually we give it a name depending on the base that we're dealing with. So we would call this the decimal point. This holds a weight of 10 to the minus 1, which is basically 1/10. This holds a weight of 10 to the minus 2. This holds a weight to the 10 to the minus 3. Now, we call this base 10. Now, why we call it base 10 is that that's the base of my exponent. So we call it base 10. So this is the decimal number system, or what we refer to as the base 10 number system. So this is true for any numbering system, guys. What we just did is true for every numbering system out there, except this is base 10. So base 10, what do I use as the base for my exponent? I use 10. Base 2, I'm going to use 2. Base 16, I'm going to use 16. Base 8, I'm going to use base 8. When I went to college, we developed the numbering system. It was a base 24. Instructor wanted to do a base 24. And then we had to count in the hands. Everybody okay? So that's why we call it base 10. So this is what they're showing us right here. This chart should be in the book. I don't know what page it's on. But 10 to the 0, any number raised to the 0 power is 1. If you don't believe me, put a billion in your calculator, raise it to the 0 power, and you come up with what? 1. Then we have 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth, 10 to the seventh, 10 to the eighth, and we can go on to infinity. On the other side of our radix point, we have 10 to the minus 1, minus 2, and then they show the actual number that it represents. So this is using what we call positional location, where we can take the value of the 6 and multiply it by 10 to the third, take the 3, multiply it by 10 squared, take the 1, multiply it by 10 to the first, and take the 0 and multiply it by 1. Right? Now what I've done here is we've taken this and converted it to the actual physical weight of this number. So 6 times 1,000 plus 3 times 100 plus 1 times 10 plus 0 times 1. Right? You understand? And then we add all of them together, and then we come up with the way that this is called writing a number positional rotation. If you understand this, guys, you can understand, you can make up a base. Now the bases we're dealing with, of course, we're not going to get away from the decimal numbering system. Why? Because that's the numbering system you understand. That's global. So fractional numbers. So this is 0.812. So 0.812. This is the way it would be written in positional notation. Since this is the first one on the other, this is 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. If we kept going, it would be what? 10 to the minus 4, minus 5, everybody okay? Then we'd write down the decimal equivalent of this, multiply it out, and then you add them together, and this right here will come up and give us a number. Now you say, why are we doing that? We're starting off with 0.82 when we're ending up with 0.82. What we're going to do is we're going to see how this will work going from other bases besides decimal. Real numbers have weights that are both positive and negative powers. We have what we call an integer. What's an integer? Yeah, but it's a number that has no fraction. And then it has a fractional part, right? It's called a real number. Now, when we get into PLCs, real numbers, Alan Bradley, which is the PLC we're using, or don't call them floating point numbers. And what do we mean by a floating point number? So when I deal with money, so a fixed point, so if I go out there and look at a cash register, it's what we call a fixed point number. Right, you understand? So that means in money, we always have what? 2 digits on the left, and then we can have multiple digits on the right. This is a fixed point number. It's always those decimal points, always 2 on the left, right? You understand? And then we can extend the right. This is what we call a fixed point number. A floating point number means the decimal point has the ability to do what? Yeah, it has the ability to move within the number. Right? Everybody okay? So floating point number means it has the ability to do what? Move between the number. These are also called real numbers. Siemens calls them real numbers. Alan Bradley calls them floating point numbers. Real numbers in PLCs are the ones that have the ability to use exponents. So that means once you get up above a certain, it's like your calculator. You know, your calculator can only display so many digits. When you exceed those digits, what does your calculator automatically do? It jumps into scientific notation, right? You understand that? Of course, so it allows us to deal with very big numbers, but the problem with scientific notation is the numbers are not going to be as accurate because we start rounding, right? Everybody understand? So real numbers in PLCs, these are the numbers that can have fractional parts, right? You understand? So they can have real whole numbers, fractional parts, and also they can use engineering notation or scientific notation. A PLC uses regular scientific notation. Digits to the left of the decimal point represent the whole number part. I don't like them called, the book calls it the integer, but the way I learned it, an integer is a number without a fraction. So what they should have said, it's the whole number part of a real number. So we have a whole number, right? And then we have the fractional component. So this guy right here is not quite doing it the way I thought. Are we okay? So real numbers can have a whole number part and they can have a fractional part, right? Y'all understand that? Integers, these are whole numbers. Have weights that are positive, positive powers of 10. A number that has no fractional component can be positive or negative. So integers can, so we have what we call absolute value. What's the absolute value of a number? Doesn't have a sign, yeah. And so we can deal with those in PLCs too. Number systems, a written system for expressing numbers that is a mathematical notation representing numbers of a given set using digits of other symbols in a constant manner. These are the number systems that we use inside PLC. We use decimal, of course, right? This is the numbering system the PLC uses. Right? Understand that? So every other number system that makes it easy for me to use, the PLC is going to have to translate it over the byte. So we'll be able to use a decimal number system, and usually this is transparent to me. How many of y'all use a decimal number system on your laptop or on your phone? That phone, the processor inside that phone has no idea what a decimal 1 is, or a decimal 2, or a decimal 3. All it understands is what we call the binary number system. But what you have to realize is, this is in the slide later on, is that a computer has the ability to process information with programs. And all this up here is just a series of dots. It's hard for y'all to see, but if you would come up real close, you'd see these little tiny squares up here. So this is not actually an O. It's just a series of dots that the computer either turns on or turns off to make it look like a Y, look like an O. Actually, this is represented in the computer by a pattern of ones and zeros. And then the computer takes that pattern and just turns on dots up there to make it display on the screen. So your computer has no idea what the decimal number is. All it understands is the binary. But we have to have, if we're going to deal with this, then of course this is what we like to have, right? But we have other methods too where it can deal with very large and very small, very large binary numbers. So everybody okay? So, you know, everybody okay with base, the base of the number system? Anybody got any problems there? Right? Everybody okay? I'm sure are quiet. Any questions? We so far? Okay. Tyler's okay. Some facts. A processor and a computer only understand numbers and codes represented as a binary number system. So on my keyboard, when I press the letter K, the keyboard controller sends a binary code to the processor. And then the program interprets that to mean different things. All images displayed by the computer are a series of dots that are either what? On or off. I meant to bring my big microscope. I got a flat microscope that you can actually look at the screen of this computer and actually see those dots. Color screens use 4 colors. Anybody know what the 4 colors are? Red. Not yellow. Yellow is very seldom used. There's one computer there's one TV that said they did yellow, but most of the time you couldn't tell the difference. Black, most people forget about black. Black, red, green, and blue. And that's the 3 colors, 4 colors that you use. Black, so this is why your screen has a black background on it. So all it does to get black is it turns off the red, green, and blue, and then you see the background and it's white. fact. So I'll try to remember to bring that over. It's really interesting. But up here you can actually see the little dot. Computer programs can process binary codes into what? A series of dots that the computer uses to display images on the screen. This means the computer can display binary, they can display decimal, they can display hexadecimal. It all depends on the application that's running that puts those dots up on the screen. Very okay. Even your TV, bro. So these are our numbering systems. We have decimal, which is a base 10. So how many combinations, digit combinations do we have? We have 10. This is the one we're familiar with. We have a numbering system that the computer uses called binary. It's only got 2-digit combinations. It's what? 0 and 1. Octal has 8 combinations, 0 through 7. And then hexadecimal has 16 combinations. It uses the same numbers that we use in the decimal number system until it gets to 9. And then we use A, B, C, D, E, F. Okay? Okay so far. We're going to come back and pick on these. So these are the 4 numbering systems that a PLC uses. Octal, we don't use octal in these machines right here anymore. The computer usually displays decimal or it displays binary or it displays hexadecimal. If you ever heard of something called a registry, I'll stay out of the registry if you don't know what's going on. But that's the configuration file for the computer. And there's a lot of binary stuff in there as far as what it does to configure when you load it in that you would really have to understand. It uses hexadecimal a lot for technicians, and I'll show you some places where we can look at that. But this is actually what's being displayed. This is what the computer's displaying to us so we can understand it instead of throwing a bunch of 1s and 0s up on the screen. So binary. Here's the advantage of using binary. Used by computers and digital devices to electronically transmit, store, and process information. It's very easy to electronically transmit and receive very accurately. It's easy to electrically store for later use, and everybody knows memory, right, in your computer. All it does is store 1s and 0s. Electronically perform math and logic. The circuits that are required to do binary math are not complicated at all. The disadvantage is it requires a lot of digits to represent decimal numbers and codes. So octal, this is used by computers to display large binary numbers with what? Fewer digits. What's the first higher level numbering system used by computers and PLCs to represent binary? So this is why most of your PLCs still support octal. Because this was the first, and we like to make things kind of downwardly compatible, right? You understand? And then, but it's hard for us to understand until after y'all take tonight's class. Hexadecimal, used to represent large binary numbers and codes with fewer digits than decimal or octal. After decimal, this is the most widely used numbering system for us, right? Represent binary numbers and codes. And it's for the average person, it's hard for most users. So the binary number system only has a base of 2 combinations, right? It has a base of 2, it's a base 2 number system. Only 1s and 0s are presented. All binary numbers are created from a combination of discrete integers. So this is where we start getting into problems. So this would be an example of a binary number system. Now what I do, since this is a legal decimal number, this number right here uses the same digits that would be in all of our bases. So what I do when I'm up here teaching is I always make sure that you understand the base that I'm working with. So what I usually do is come over here and just put a little, what happened to it? I just come over here and put a little 2 down there. That just lets you know that this is a base 2 number. And we don't separate these things with dashes or dots or anything like that. So this would be a binary number. Is this a big number or is it a small number? Well, it depends. It's what we reference it to. Is it over 10,000 or less than 10,000? Well, see, this is the problem we have. Because what we're doing is we're basing our thoughts on the base 10 number system, right? You understand? This is not the base 10 number in this system. This is the base 2. Everybody okay? Yeah, this guy's less than 1,024. We'll look at it in a minute. So this is what a binary number appears like, unless we had a fractional component. So if I had a fractional component, then we would come over here and do this. Now, what this does, and let's don't play around with the fraction right now. So this is what we call the base 2 number system. So that means each one of these bits, we don't call these digits, by the way, we call these bits. Everybody okay? And each one of these bits holds the weight of the base. What base is this? Base 2. So I'd come up here and I'd start with 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th. That's not 25. 2 to the 7th, 2 to the 8th. I didn't jump over one, did I? Everybody okay so far? Now this is nice to know. So if I wanted to know this one, this would be 1 times 2 to the 8th. This would be 0 times 2 to the 7th. And any number times 0. I don't care what 2 to the 7th is.
I believe you skip that third one to the right.
I need to spread it out. In fact, let's use I'm gonna go to a smaller number anyway. So we can. So this would be 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th. So this I could spread it out and make it good. But I know this holds the weight of 2, 1 times 2 to the 4th. This is 0 times what? 2 to the 3rd. This would be 1 times 2 squared. This would be 0 times 2 to the 1st. And this would be 1 times 2 to the 3rd. Okay, everybody's okay so far? Now what we're going to do is we're trying to get, this is the way it is, right? Everybody understands this. But what we can do real easy with binary is instead of doing powers of 2, we can use the decimal equivalent of power of 2. Everybody okay? Because 1 is 1 in all these number systems. So what I'm going to do is I'm going to come up here and I'm going to erase those powers of 2s. And I'm going to come over here and put what they would be equal to in the decimal number system. So any number raised to the 0 power is what? 1. 2 to the 1st would be 2 to the 1st would be what? 2. 2 squared would be what? 4. 2 to the 3rd would be 8. 16. Can you see how this goes? What would the next one be if I added another bit? 32, 64, 128, 256, right? 512, 1024, 2048, 4096, 8,192, 16,164. We just keep coming up and double them every time, right? I can tell I've dealt with a binary number system. Now, what I would do now, guys, is now I can say, so what we did is since ones are legal in both number systems, what did I just do? I took instead of using powers of twos, which is what it actually is, I put the decimal, what the decimal equivalent is. So what would this be? Well, if I wrote it down in positional notation, this would be 1 times 16 plus, which is a waste of time, 8 times 0, right? Plus 4 times 1 plus 2 times 0 plus 1 times 1. But what are these guys right here? Yeah, there's a 0, so I'm going to use that. And what's 1 times a number? So what I can do to get the decimal weight of this number, I can say, just write down the equivalent tens, right? The powers of tens for each bit that's only got what in them? 1. And I would add those together. And what do I come up and get? 21. So this number right here is equal to 21. They are equal. What we're doing is we're looking at them in two different bases. And that's all there is, guys. Going from binary to decimal, that's all there is to it. So y'all do that one for me. And those two numbers are equal, right? You understand that? What do you mean? Yeah, I want you to make sure. This number right here, if I was to come up here and write down this number right here, what would be the first thing you would assume? You would assume it's base 10, right? Because that's what our brain works in. So what I'm making sure is that we understand the base. So this number right here, that would be a legal number in hexadecimal.
So you're just using those numbers to represent that.
Yeah, to make sure you know.
That is decimal.
This number would not be legal in octal because the biggest digit we can have in octal is a 7, but this guy here would be legal in base 16. And they're not going to be, so a 9-0 in base 16 would be a lot bigger than 9-0 in base 16. We're going to work some more. The least significant bit, what's the least significant bit? It's the number to the what? Far right. The most significant bit is the number to the far. By the way, the guy in the book used an uppercase D. I learned not to use an uppercase D. We usually use an uppercase D to represent something called a byte, which we'll look at in a minute. So this is like base 10. Converting binary to decimal, that's pretty easy. So all we have to do, I could come up, I'm not going to come up with big numbers, but it's all the same. So what would we do if we came over here on the other side of the binary point? Well, if this is 2 to the 0, 2 to the 1, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth, then what's this guy going to be? This is going to be 2 to the minus 1. This is going to be 2 to the minus 2. This is going to be 2 to the minus 3. Everybody okay? So I need to know what 2 to the minus 1 is. Everybody know? By the way, to get the minus value, what you would do is it would be the reciprocal of this. So that'd be the reciprocal of 2. The other would be the reciprocal of 4. The other would be the reciprocal of 8. This is also true on the base 10 side. So what we would do is this right here would be equal to what? 0.5. This right here would be equal to 0.25. And this right here would be equal to 0.125. So what's going to be the weight of this number? Come on. Give it a shot. That's not the same number as before, is it? No. Go do it for me. As far as the recording. Well, this halves every time. So notice, you start off with 0.5. What's 1/2 of 0.5? And then what's half? What would be 1/2 of this? 0.065, right? We have different ways we can do this. We can do it by repetitive. To go from decimal to binary, we can use what we call repetitive division. Or we can use what I like to call successive subtraction. So repetitive division would mean I would come up and have a number. So let's do 287. And this works, by the way, going to any base. It's just base 2 is a little easier. And then what I'm going to do is I'm going to divide this by 2. So what's 287 divided by 2? Huh? What's that? 0.5. Well, every time I have a 1.5, every time I have a 0.5, I'm going to write a 1 over there. Because that's what it is. And then what I'm going to do is I'm going to take this and divide it by 2. And what does that give me? I'm going to write 71 down here. And I'm going to put, every time I have a 0.5, I'm going to put a 1 over there. Every time it comes out to be a 0, I'll write a 0 there, right? I'm going to divide this by 2. What does that give me? Everybody follow me so far? I'm going to divide this by 2. What do we get? I'm going to divide this by 2. And what do we get? I'm going to divide this by 2. And what do we get? No, 8 divided by 2. What's that? I'm going to take 4 divided by 2. And what's that going to get? What's that? It's going to give me 2, right? And then I'm going to take 2 and divide it by 2. And what does that give me? I'm sorry, it's going to give me 1. Sorry. And then I'm going to say 2. 1 divided by 2. Well, what does that give me? 0.5, and I write a 1 down there. Now I got all these 1s and 0s out here. And what do I do with that? Anybody know? We let it fall this direction right down here. So I'd say 1, 0, 0, 0, 1, 1, 1, 1, 1. Now let's check our work. So this would be what? 2, I'm sorry, this would be 1, 2, 4, 8, 16, 32, 64, 128, 256. I'm going to add 256, 16, and 15. 8, 4, 2, 8, 4, 2, and 1. 256. Duh. Add those together. What do we come up with? Hopefully it came up to be 287. This is a 1. So this is called successive repetitive division. Now let's do it another way. And by the way, this works with any base. It's just that when we divide by 2, when I get 0.5, that's actually means we have a whole number remainder of a 1, right? You understand? So you can take your remainder, multiply it by the base, and that gives you the whole number remainder. This works for any base, but when you get into base 16, it gets very, very complicated. We're not going to go between the decimal numbering system and base 8. We're not going to go between the decimal numbering system and base 16. We're going to learn why we use hexadecimal and why we use octal. And that's to give us the ability to represent these big old long binary numbers. So let me get a blank page. So what I would do is I would come up here, and people get this reverse, guys, for some reason. But what was the number? 287. And this is base 10. What I will do is I'm going to come up here and I'm going to make up a chart. And I'm going to write down my decimal equivalent of my powers of 2s. I'm going to say 1, 2, 4, 8, 16, 32, 64, 128, 128, 256, and then 512. I always go one pass. Now, for some reason, people want to do this. They want to subtract this over here, but this is what we're going to, right? You understand? So what we're going to do is I'm going to come over here and find the highest. Now, I always go one past my number to make sure I got enough bits up here. We're not going to use this guy right here. Right? So what's the biggest thing that I can subtract from 287? 256. Well, what I'm going to do is I'm going to put a 1 up here. And I'm going to come up here and I'm going to subtract that highest thing I can subtract. And what does that leave me? 31. Right? Can I subtract 128 from 31? Okay, so I'm going to put a what? 0. Can I subtract a 64 from 31? No. Can I subtract a 32 from, okay. Can I subtract a 16? How many times can I subtract it? If you ever say I can subtract it twice, you screwed up, right? You're either not going to subtract it. If you can't subtract it, you're going to put a 0. If you can subtract it, you're going to put a what? 1. So I'm going to subtract my 16. What does that leave me? 15, right? Can I subtract an 8? Okay, so I'm subtracting 8. Okay. Can I subtract a 4? I'm going to bring this up here. Okay. Write that down. Give me 3. Can I subtract a 2? Can I subtract a 1? Now, if you run out of numbers before you get down to the 2 to the 1, you fill these in with 0. Here, this came out to all the way out to the E, right? But if I was to end up subtracting right here, right, you understand, then what would I do? I would fill those in with 0. Everybody understand? Now look, we came up with the same binary number we did before, but to me, guys, this is so much easier. When did y'all learn how to subtract? First grade? By the way, another little telltale sign. This right here, these are all even numbers. If I add an even number plus an even number, I always get an even number, right? If I add 2 odd numbers, I get an even answer. But we don't have 2 odd numbers. The only odd number we have is this guy right here. So if this guy right here is a 1, you better come up with an odd decimal number, because this determines if the decimal number, if the binary number is even or odd. So if I'm taking an odd decimal number and I come up here and end up with this as a 0 down here, then your answer is wrong. Right? It don't mean it's It don't mean it's right if it ends up with a 1, but it's it's definitely, wrong. So an odd decimal number has got to be an odd binary number, right? You understand? And an even binary number an even decimal number had better come up and give you an even binary number. So let's do one. So what number y'all want to do? Huh? Let's do a little bigger. Let's do 1,464. Is my number. So I'd say 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024, and I go 2,048. I usually go one pass to make sure I got enough bits out there, right? That makes sense. It's up to you. So how many of these decimal numbers you use, or power that you use, depends on the size of the number. Somebody's got it. Wait a minute. What'd you come up with, Kareem?
1 0 1 1 0 1 1 1 0 0 1.
Did I write that down right? Or, okay, that's what Kareem got. Now look.
3 1.
What do you mean 3 1? Where?
Right
Right here?
No. Then you put like all for 1, you put the 3 1, and then 0. Oh, it should be 0.
Right here?
Yeah, take it.
Put a 0 right there? Yeah, I was just saying.
Now, last one. One.
This can't be a 1.
You got 0.
Now, how do we know that? Yeah, it's an even number. That's it? That's it?
I mean, it's not an odd number, so it shouldn't have a 1.
Now you saw how much problem we gave that out. Now which one would have been easy for me to give? And you write it, you get it, me get it down. 5B8 or 101101110. If I was going to convey this number to you, which one would be more easy for you to comprehend? 5B8. What I just did, guys, I went to hexadecimal with that number. We'll look at that. Could have went to octal. So we want to work it. So what would I do? Take the biggest thing I can buy and subtract from this. We're not subtracting from this, we're subtracting from this. That's what happens. That's one of the biggest mistakes people make, is they try to subtract that from this. That's wrong. Right? You understand? We're going to subtract this from that. So I'm going to look at the biggest decimal equivalent I can find, and what's the biggest one? It's going to be a 1. Okay. And now I'd write down 1,024. And I would subtract that out. What does it give us? Then I say, okay, can I subtract a 512? Okay, so I'd put a 0 right there. Can I subtract a 256? What does that give us? What's that? Can I subtract the 128? What does that give us? Can I subtract the 64? Can I subtract the 32? What does that give me? Can I subtract the 16? Can I subtract an 8? Now, guys, you got to come up and get this. You got to come up and get this sooner or later. If you run out of digits and you're still subtracting, right, you understand you did what? Did something wrong. And what do I do now? So I wrote my 1 into 8, so what do I do? I got to fill in the remainder with zeros, and there's our number. Okay, guys, let's take a 10-minute break. I'm going to pass the break time inside your computer. That you didn't know. So we okay? You want to do another one?
When you do hexadecimal, you start at the left side.
Always. We'll get there in a minute. Yeah. So this number in hexadecimal. I'm just going to come over here. Know what? 1, 2, 3, 5. I'm going to set it up in groups of 3s. That'd be 5, B, 8. And you can say it's a lot easier to give it out that way, right? You understand? So if a computer wants to display large binary numbers, odds are it's going to give it in, and you got to know the binary number. Now, of course, we like everything to be in decimal, and everything that we're going to do with, and we're not going to be doing any math. We're going to do logic, but we're going to do it with contacts. So in this semester, we learn how to do logic with contacts, which is what we would do if I was going to do logic with a motor control circuit. I would do it with contacts, switches, kind of like light switches. But that limits what a computer can do, right? So a computer can do a lot more, and this is what we get into in advanced PLCs. We get into the actual computer. So everything we do in this class, we could do with relay logic, except for the counters. And then in advanced PLCs, we get into the math, add, subtract, multiply, divide. We get into long logic instead of 1 bit. And we'll look at that. We get into sequencers. We get into shift instructions. We get into compare instructions. We get into what we can't do with relays, what we can't do with hardware. Everybody okay? Want to do another? So let's do an odd number this time. So let's do 785. So what'd you get, Kareem? Slow.
1, 1, 0, 0, 0, 1, 0, 0, 0, 1.
What we got? Everybody okay? You get something different, Tom? We okay? Anybody want to see it work? Okay, so we'll start off with our chart. I'll go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. And like I said, what's the general mistake people make? They want to subtract this from this, and I don't know what to tell you. We're not going from there to there. We're going from here to here, right? So I'm going to look at the biggest thing I can subtract. What's the biggest thing I can subtract from 700? Okay, so I'd put a what? And then what does that leave me? 273. And I subtract the 256. Okay, now you got to remember to write this 1 down over here. Every time you subtract, you write a 1 over here. I've seen people do that. They forget to write the 1 over there, and then they're off of whack. 256. What does that leave me? What's that? 17. I can't subtract the 128. I can't subtract the, did you say 17? Can't subtract the 64. Can't subtract the 32. Can I subtract the 16? Okay, put a 1. 16, what does that leave me? Can I subtract an 8? Can I subtract a 4? Can I subtract a 2? Can I subtract a 1? And that's it, guys. To me, that's so much easier than the divide method. Because all you do is start at 1 and just do what? And you'll have this chart, by the way. This gives you powers of 2s all the way up to, I do okay up to 2 to the 16th, and after that, I get lost. But that takes you all the way up to 2 to the 40th. And that's not even, we're dealing with 64-bit processors now. Our PLCs usually don't have that because they don't need, what the biggest thing that we have, what we do is this right here, this graphics. This takes up so much time and so much speed and processing power. Originally, the microprocessors had a arithmetic logic unit that did everything, but now most processors have a graphics processor in there that's just in there handling what? Graphics, turning these bits on and off. You know, if you got 1024 by 768 at 32-bit color, just think about the amount of memory space you got to go through and update those dots. It's unbelievable. So PLCs don't deal with graphics. I mean, they're 1s and 0s. So that means we can drop the memory down and we don't have to use these big, powerful processors anymore that runs up in the gigahertz range and that kind of stuff. So PLCs are basically binary. This is where they depend on, this is what they depend on. They depend on you do all your programming on a computer that can do what? The graphics. And then what you do is when you download it into the PLC, it translates it over to binary for the PLC. When PLCs first came out, we didn't have computers. The CPU in the PLC did everything. They had all the graphics and all the other kind of garbage in there. And we had dedicated terminals that we used to program it. That's all you used them for. We call them dumb terminals. You hook them up to the thing. They wouldn't do anything until you hooked them up to the PLC. So the PLC had to support the graphics for the terminal, right? You understand, but not anymore since we've got this right here. So we're going to program in graphics. We're going to use a lot of decimals in this class. Are we okay? Yes, no? Okay, so this is counting in binary. This is decimal right here. And we do the same thing. We start with 0, we go to 1. I've run out of combinations. What do? I put a 1 out here and do what? Start over. 1, 0, by the way, in any base is equal to the base. So what's 1, 0? What's this digit combination in base 10? 1, 0. It's 10. 1, 0 in base 2 is 2. So 1, 0 in base 8 is going to be 8, right? You understand? 1, 0 in base 16 is going to be what? 16, right? Then I go 1, 2. I've run out of combinations. What do I need to do? Add another bit and start over, right? You understand? Then I go 5, 6, 7. I've run out of combinations. What do? Stick another 0 there and start over. 8, 9, 10, 11, 12, 13, 14, 15. I've run out of combinations. What do I need to do? Add another 0, start over. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. I've run out of combinations. What do I need to do? Yeah, just start over. And so what you learn in the base numbering system, this is the same thing we do in every numbering system, right? It's just that we got to understand the number of digits that's available to us in that base. Everybody okay? And I took this all the way up to 63, but here's 63. What would I do? I'd add another 0 and start over. Binary addition. So binary addition, let's add some numbers in binary. 1, 0, 1, 1, 0, 1, 0, 1. I'm going to add 1, 1, 0, 1, 0, 1, 1. What's 1 plus 1? I can't have a 2 down here. So I'm going to put a 0 with a carry of 1, just like I did on base 10. What's 1 plus 1? 0 with a carry of 1. 1 plus 1 would be what? 0 with a carry of 1. 1 plus 1 would be what? 0 with a carry of 1. 1 plus 1 would be 0 with a carry of 1. 1 plus 1 plus 1. We're going to be 1 with a carry of 1. 1 plus 0 is 0 with a carry of 1. And this is going to be, we just write it out. So in binary and decimal, we carry a 10. Here, every time we're going up, we're carrying a 2, right? Huh? Now we could convert these over. Huh? But look how easy it is. So 1, okay, 0 plus 0 is what? A 0. 0 plus 1 is what? 1. 1 plus 0 is what? 1. 1 plus 1 is what? 0, because that's 2, right? With a what? With a carry of what? And then 1 plus 1 plus 1 would be 1 with a carry of 1. So 0, I mean, most of them, so 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, plus 1, 0. We could convert these to decimal, but now you're taking a bunch of time. So what's 1 plus 1? Wait, let me clean this up a little bit. So 1 plus 1 would be what? 0 to carry 1. 1 plus 1 is what? 0 to carry 1. 1 plus 0 plus 0 is what? 1. 1 plus 1 is what? 0 with a carry 1. 1 plus 1 plus 1 is 3. Yeah. 1 plus 1, 0 with a carry 1. 1 plus 1, 0 with a carry 1. 1 plus 0 plus 0, 1. 0 plus 1, 1. And I guarantee if you converted those over to decimal, that would be the right answer. So that's adding in binary. Now in base 10, when we subtract, when we have to borrow, what do we borrow? We're borrowing a 10. A lot of people say you borrow a 1, but you're borrowing a 10. So in base 2, we're going to borrow a 2. We're going to make sure the top number is bigger than the bottom number, because we're not going to explain Fick's complement in this class. There we go. So this is a little chart. I think this is probably your book somewhere. Are we okay? So y'all add something. So let's do 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1. What's the problem the longer we put these numbers out there? What are y'all doing? So, so this is the problem we have if I'm trying to convey big binary numbers, is that most people have to do what? Write down a couple, write down a couple, write down a couple, right? We're going to drop some of those off. Huh? And we'll look later. I'll show you how to do. I'll show you how to do hex math too, if you want. So let's drop some of these off, guys. Let's drop these off. And what do we want to add to it? Same number of bits. A little easier. So that would be F5 and D1 if I do that hex. This is what they use to search track to. So starting at least a bit, at least an a bit. What we got? Huh? Is that right? Everybody okay? Yes, no? For me, it's easier to add and by. And the little circuits that do addition, I mean, good gracious, there's nothing. This would be a circuit that would add 2 binary bits. If this was decimal, so that's the little circuit right there. This handles the carry, this is the adder, and that's the little digital circuit that would add a bit. Nothing to it. How would I come up with a computer that could add 6 plus 7? Right, you understand? How would I make an electronic circuit that would add decimal numbers? Basically, it would be very, 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 very complicated, right? I don't know if y'all got into some of the old adding machines that did it with gears. Y'all ever look at those things? Man, that was amazing. Whoever figured out how the original adding machines were gears. Yeah, yeah. So this is the circuit. This is an adder right here. That little circuit right there is an adder. That's a digital adder. Now, what's nice about this, though, is we can represent this electrically. We have 2 methods we can represent electrically. We can either use an electrical current or we can use electrical voltage. And by far, the most method widely used is the voltage. So I could come up here and so this would be a voltage I put in it. So this right here might be 5 volts, 5 volts. This right here would be what? 0, 5, 0, 0, 5, 5, 0. And that would be I would bring that into this circuit and it would give me an electrical answer, but that answer would be binary. So what's nice about binary is, and what I like to use as far as transmitting data, think about me having a flashlight that I've got 10 brightnesses on it, representing the decimal number system, 0 to 9. You go across that street over there and I turn my flashlight on one of those things. How many people would be able to tell what I'm trying to say? Almost nobody, right? You could guess at it. How many of you could tell if the flashlight was on or off? Right? Y'all understand it? How far could you get for me to flash a flashlight at you and tell if it was on or off? Well, what I'm doing now is I'm conveying binary information, but I'm doing it with a flashlight. I could use 8 flashlights, right, and put them far enough apart so you could tell them, and I could send you binary numbers. So that means if I can represent these things with dosages, I can send them, over great distances. I can process them. I can add them. I can subtract them. I can do ands. I can do ors. And the circuits are very, very simple. Dealing with the base 10 numbering system, doing math electrically, trying to come up with a circuit that does it is really, really complicated. 5 volts, by the way, is a standard level. Our computer uses 24 volts and 0. So how would we subtract these things, guys? Oops. Somebody give me some ideas. So 1 minus 1 is 0. 0 minus 0 is 1 minus 0 is 0 minus 0 is 1 minus 1 is 1 minus 1 is 0. 1, 0. Now that was pretty easy to do because we didn't have to do a borrow, right? So when we borrow, what are we going to borrow? We're going to borrow 2, right? No matter what the book says, we're going to borrow 2. So let's come up with one that we're going to have a borrow on. So I can't subtract 0 or 1 from 0. What am I going to do? I'm going to mark that out. This will turn a what? 0. This will turn in a 2. Because we borrowed a 2, right? You understand? 2 minus 1 is what? 1. 0 minus 0 is 0. I can't subtract this. What do I need to borrow? Come over here, mark this off, makes this a 0, makes this a what? 2. 2 minus 1 is 1. Can't borrow from this. What do I need to do? I need to come all the way up here. It's going to make this a 0, right? It's going to make this a 2. Borrow from 2, it's going to make it a 1. Makes this a 2. Borrow from that, makes it a 1. Makes this a 2. Everybody okay? 2 minus 1 is 1. 1 minus 0 is 1. 1 minus 1 is 0. What do I have to do right here? Makes this a 0, makes this a 2, and there it is. So, I mean, it's not, to me, it's so much easier to do binary addition than it is in subtraction. It is to decimal. Because here you're always borrowing a 2, right? And you're only subtracting 1 from 2, or you're subtracting 1 from 1 or 1 from 0. Now multiplying gets interesting. But we had one of our students one time showed me a trick, and it's so neat. We'll have to show it to you. Okay, so subtraction next. It said, so y'all do this subtraction. So we need to make sure the top number is greater than the bottom number, because the way a computer represents signed numbers is really weird. So it's obvious that the top number is greater than the bottom number. Now take this home and show your spouse or show your kids, it's going to freak them out. So at base 8, we would borrow an 8. At base 16, we would borrow a 16. But that's rough. But we're not going to do math in the other higher bases. If you're in ILT, you'll take digital to go through this again. In PLCs, so this is that nice to know stuff. They're really, this is what the book teaches this. So. But I've never ran into it trying to do binary math with a PLC. So anybody got it? Where do I need to start at? Right here? So what we got? Where do I need to start at? Let's work from the right. We usually don't call numbers out from the right to the left. It just makes it easier to write them down. So what we got here? Listen. Pick 0. No 0. Okay? All right? Huh? Sure. So right here, I say 0 minus 1. What do I need to do? So I'm going to make this a 0, make this a 2, and I give a 1. Can't get this guy, so what do I need to do? Borrow from here, makes this a 0, makes this a 2, borrows from that, makes it a 1, makes this a what? 2. 2 minus 1 is 1. 1 minus 1 is 0. 0 minus 0 is 0. 0 minus 0 is 0. 1 minus 1, 1. Got to borrow here, right? Mark this out, makes this a 0, makes this a 2. 2 minus 1 is 1. Okay. Now multiplication gets a little complicated, and why is that? So there's subtraction, right? Here's subtraction. Then we played around with that. Here's multiplication. Well, how do y'all think we're going to multiply? All the rules, by the way, work. All the rules work. So if you have a 0, you can shift it over. You put a 0 down, shift it over. So what's 1 times 1? So I start here. I multiply the least significant bit first. What's 1 times 1? What's 1 times 1? What's 1 times 0? What's 1 times 1? What's 1 times 0? So what I do, every time I got a 1, I just write down the original number, right? So you don't have to learn multiplication tables because it's either what. So I would come down here on my next one. I would just come down here and fill this in with 0, so I could shift it. Then I would come down here and I would just write down my number. So in multiplication tables, what's binary multiplication tables are really neat.
I think we got a 0 on that bottom.
Yeah, we did. I'm sorry. I just seen if y'all was paying attention. So 11101, right? Then add them, guys. What do we come and get? Oh, by the way, what did you learn in multiplication? Anytime you got a zero, you didn't have to write the zeros down. You could just what? Just go over to the next power, right? You understand that? Yes. I mean that's fine. You was taught to write the zeros? Okay, that's fine. So what do we got? 1, 1, right? 1, 0 with a carry 1, right? 1, 0 with a carry 1, 1, 1. Now, of course, here we're only doing 3 different ones. You get the bigger the bottom number gets, and the top number gets, the more complex. But the further you go down, the more ones you're going to have to add. Now, and I used to do all that, but somebody brought something up to me. This is a student that came up with this problem. It's so cool. It makes it real easy to do this. I just count the number of ones. So I count the number of ones. What do I come up and get? Huh? So I'm going to write a 0 and a carry 1. And I'm going to go 1, 2, 3, 4, 5. That's going to be a 1. Carry with 4. Is that right? No, we get 1 carry right here. I'm sorry. We get 1 carry right here. Let's write this down. Okay. So this would be a carry. This would be a carry, right? You understand? And then I end up with a 1, right? So what we're going to do is we're going to come up with how many carries do we need. So here I said 1, 2, I'm sorry, I had a carry right here, right? Sorry. So for every 2, we're going to carry a what? 1. So I'd say 1, 2, 3, 4, 5. That's going to be 1 with a carry of 2. Then I'd say 2, 3, 4, 5, 6. That's going to be 0 with a carry of 3. And I'd say 3, 4, 5, 6. That's going to be 0 with a carry of 3. That'd be 3, 4, 5, and then I would just write down a 5. Now we're not going to do that. So basically, if you come up with an odd number, you write the odd number, then you divide whatever you got left by 2. So this is about as far as we go, guys. Y'all okay with that?
Yes.
Yeah.
Division, we'll just look at it. So let's say I want to divide a number. And I want to divide it by this number right here. Oh, I'm going to need more room, aren't I? So 101101. We're going to divide it by this number right here. Okay, so what would I do? I say, okay, I'm just going to look at this. Would this go into that? No. Would this go into that? Would this go into that? How many times? It's binary, guys. It's either going to go what? 1 or 0. I would write this down and I would subtract it. So this would be a 0, right? And this would be a 1. Everybody okay? And then I would bring down this guy right here. Would this go into that? How many times? One time. I'd put it above this. I'd put that down there, and I'd subtract it. We okay? I'd write down this next one. Would this go into that? I put a 1 up there, right? You understand? I would come down here and I would subtract it, right? Okay, and what would this give me? Have the bar all the way across, right? This is going to give me a what? 1. Then I bring down that one. And then I'm through. We're not going to do fractions. So to me, but what's nice about binary, we're just going to have ones and what? 0. Oh, well, this won't be on test. Multiplication won't be on test. Y'all say, well, we did it because it's in the book, right? Okay, so this is what's important there. Hexadecimal. Used in medium to large programmable logic controllers. Often called hex, which is not correct, but because hexadecimal, hex is 6, decimal is 10. So hexadecimal would be 16, right? Everybody okay? So hexadecimal is base 16. People that's been dealing with it a long time call it hex. It's okay if you want to call it hex, just as long as you understand it's not base 6, it's base 16. Used to display the PLC's memory map and carry out math instructions. This guy, we use it for logic, or we do it for masking. You have to understand how this goes to binary. Created in groups of 4 what? Binary bits. Hexadecimal was used base 16 and requires 15 digits. That's not true. It requires 16 digits. It's just that one of the digits is what? 0. Now I could show you how to convert decimal into hex by using division. We don't do subtraction. We'd have to use that division. But every time you have a remainder, you'd have to multiply it by 16 to get your whole number remainder. But we don't use hexadecimal as hexadecimal. What we use hexadecimal for is to represent binary. So first of all, we need to figure out how we're going to count, or what we're going to do with our numbers. So over here I got the decimal numbering system. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I'm going to have to make it smaller, guys. Or we'll just 13, 14, 15. So hexadecimal, we got 16 combinations. Everybody understand? Everybody okay? Now, so what this is decimal, and we'll put a D up there, and here's hex right here. So 0 in hexadecimal would be this, 1 would be this, 2, 3, 4, 5, 6, 7, 8, 9. Now I've got to represent a 10 with 1 digit. So what we do is we jump into the alphabet and we go A, B, C, D, E, and F. So F is equivalent to a decimal 15. Everybody okay? Now if I was going to count in hex, I'd go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'd go A, B, C, D, E, F. I need more digits. What do? I put a 1 out here and put a 0 right there and start over. So like I said, this is the base. That 1, 0 combination is the base. Then I'd go 1, 0, I'd go 1, 1, 1, 2. I'd go 1, 1, right? 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1 A, 1 B, 1 C, 1 D, 1 E, one F. What would come next? 2 zeros. We hadn't run out of combinations here. And this would go all the way till we got to FL, to be 255. And then I would start all over. 256. And I would keep going until I got up to what? F, 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 right? You understand? And then I'd add another digit, and I'd add another digit, and start over. Somehow my touch screen has got enabled. I usually keep it disabled. Now, what we have to understand is how do we go from binary? First of all, what we got to understand is there's a little formula where we can calculate the number of combinations a digit will have, right? It won't let me erase. Very strange. So how many combinations can we represent with 4 bits of binary? 16. So that would be 1, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and I'm through. I can't count any further without doing what? Huh? Yeah, well, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's 16 combinations. Well, how many combinations do we have with one digit of base 16? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16. So I've got exactly 16 combinations with 4 bits of binary, and I've got exactly 16 combinations with 1 digit of hexadecimal. So that means this would be equal to this in binary, this would be equal to this in binary, this would be equal to this in binary, this would be equal to this in binary. Oops. This would be equal to this in binary. This would be equal to 5, 6, 7, 8, 9, A, which is 10, right? B, C, D, E, and F. I've run out of combinations on base 16, and I've run out of combinations on base 2, unless I add more digits. Everybody understand that? So let's say I come over here. So I'm going to come over here, and I'm going to write down a long binary number. And you don't have to do this, guys. And I'm trying to give you that. What would be the odds of y'all getting this copy down? Everybody in the class copying down this copy. Pretty astronomical, right? So what I'm going to do, I'm going to do this in a different color. Is I'm going to come up here and I'm going to split this up into groups of 4s. 4, 4, 4, 4, 4. And I'll pretend there's zeros out there. And then what I'm going to do is I'm going to write down the hex digit that's represented by those combinations. So this right here would be an E. This right here would be an A. This would be a 5, 7, 5, D, 2. Because what I'm doing is I'm pretending there's 0 there. If I was to take this number and punch it in my calculator, you'd find out they're exactly equal to each other. And it only works if the number of binary combinations and the number of equivalent are exactly the same. So how many of y'all could write down 2D, 5, 7, 5A, E, and get that down? Just about everybody in class. And so if I gave you that, then I wanted to see the binary equivalent, then all I would have to do is come up here and write down these patterns. So I'd write down an E, I'd write down an A, I'd write down a 5, I'd write down a 7, I'd write down another 5, I'd write down a D, and I would write down a 2, and I've just converted that back to binary. So to go between hexadecimal and binary, all you have to do, and if you think back to elementary school, everybody understands, I don't know if I talked about it in this class, what is multiplication? Well, multiplication is repetitive addition. So I could take 5 times 5, and what it's telling me to do is I'd add 5 to itself 5 times, and I'd come up and get 25. But what did we do to get away from all that repetitive addition? You learn multiplication tables. So instead of me saying 5 plus 5 plus 5 plus 5, I just come up here and I say 5 times 5 equals 25 because I memorized that 5 times 5 is 25. And how far did you go in elementary school? 12's usually. Here, guys, all you got to do to go between these bases is memorize 16 binary patterns. If you can memorize those 16 binary patterns, you can go between these two bases without even thinking about it. Without a calculator. So if I'm a computer and I want to display a very large binary number and I want you to get it right, what can the programmer do? He can turn on the dot patterns on the screen to display it in hexadecimal. Right? This sucker right here has got like a 40-bit address bus, and I'm trying to figure out what address a device is at. You think this computer's going to display a 40-bit address bus in binary? No. So if I wanted to look at the layout of this computer, and you can do it, it's a little harder to find on Windows 10. Real easy to find on Windows XP. I can go over here to Program Files, and I can go into Accessories, and I can go down here to System Tools, and I can look at system information. And I can look at my hardware resources. These are the addresses. And I can look at memory. And this is the memory. This is what's assigned to the memory inside this computer. What base is this guy? FF04, F2, 523, 40, FF. What base is they trying to give you? Think about that number. Each one of these are 4 bits. 1, 2, 3, 4, 5, 6, 7, 8. 8, that'd be 8 times 4, right? 32 bits, right? You understand that? And if they was to put ones and zeros up there, 32 bits, right? You'll understand. But they don't. They display it in what? Hexadecimal. There's no such thing as a hexadecimal address. But the computer, the programmer, all it's doing is turning on patterns, right? You understand? So it can take this 4-bit pattern and then say, okay, this is equal to this dot pattern and display an F up there, right? You understand? Or an A. And like, people don't understand that. Computers don't understand hex. Computers don't understand decimal. Computers don't understand octal. Computers understand ones and zeros. But it can process information, right? And it can display things like they're not really, like it's not really existing inside the memory. So yeah, this is the resources. So this is the I/O addresses here. So somewhere down here is the video controller, PCI bus. It's in the 60s. Yeah, so there's a graphics controller on this motherboard. It's built into this computer. So I know where the graphics is. If I knew the codes to tell the graphics controller what to do, I could do that. In the old days, we had a this is what we used to see on our computers when they first came out. Everything was in text before they started adding graphics. This is still available even on Windows 10. This is called Command Prompt. And they had a nice little problem called debug that they don't let us use anymore. But I could dump the memory, so I'm gonna dump addresses 0. And this is what it dumps out. Now it's not gonna dump it in binary, right? You understand? It's gonna display it in hexadecimal. So this is we're actually looking at the contents of the RAM memory inside this machine. So this is what's in there, but it's binary. But when debug displays that information on my screen, it's not going to do it in binary. By the way, 2 hex digits. How many bits would each one of these represent? 8 bits, right? 8 bits, 8 bits, 8 bits. Now notice over here on the right hand side, I have some weird stuff going on here. So if I know what's going on and I know how the computer works, so now I'm in a level. So what I'm doing now, I'm looking at the video menu. What I just did is I've addressed this guy right here. And I'm going to come up here and I'm going to enter a code up there. See the little M pop up there? So this is what we're talking about, but you don't have to know the addresses for your video, right? You understand? You don't need to know the codes because all this is taking care of your operating system. But what I'm trying to show you is that everything the computer does is in binary, but when it displays this information for you, it's probably going to do it either normally hexadecimal. By the way, when they came out with Windows 7, they took away debug. So don't go home and type in debug. If you got a Windows XP machine, it still supports debug. This is dangerous. You actually got low-level access to everything in the machine. We used to get into the error message section and make it display error messages. I'm embarrassed about that because I'm not going to tell you some of the things we had inside. That was in my younger days. So let's convert some. Where's my PowerPoint at? So okay, guys, let's take another. What time does this class get out? 9:30. Let's take another 10-minute break. Now, we try to go about an hour. You can see me when I get kind of involved. So about every hour, what do somebody in here need to do?
Say something.
No, don't say something. Just do it.
I got you. Every hour.
About.
Every hour.
It's hard to go from binary to hex because it's hard to get the number down correct, right? So let's see if y'all can go from hex to binary. So y'all got y'all's patterns. Y'all got y'all's little handout, right? Don't it have the hex patterns on there? But if you're going to deal with PLCs or deal with computers a lot, and this is what you need to do. They deal with hexadecimal. This is still the primary method. The reason why PLCs first came out, they did the optimal numbering system, was, of course, that was the first one they used for 8-bit processors, or 8-bit processors. When the first processors came out, they were 4-bit, then they went 8, and then they started jumping in groups of 8s, right? 8, 16, 32, 64. Then they found out that the hexadecimal number system was just more efficient. So let's go ACB9. This is base 16. We want to go over to base binary. So if I'm going from binary to hex, I just divide it into what? Groups of 3s. Groups of 4s. Starting with the least. You just can't start any way you want to. You can come over here. You always start on the right-hand side, right? For the whole numbers. So what do we got? Anybody got it? No, you don't get A, C, B, 9. See, I did it better for me to give it that way. So if I was to come up here and I said, I'll do it about the same speed. I said, okay, everybody write this number down. 1, 0, 1, 0, 1, 1, 0, 0. 1, 0, 1, 1, 1, 0, 0. Who would have got that right? Nobody. But if I would have said A, C, B, 9, same speed, everybody in the class would have wrote that down if you wasn't asleep, right? You understand? So if I'm going to convey a big, large binary number to you, then it makes sense if I can give it to you in hexadecimal. Everybody okay? So let's just do an 8-bit number going over here. So I'm going to come up here and put what would that be in hexadecimal? BC of Washington. Direct current. This is what gets people in trouble. They'll see a number like this. And the first thing that pops in your mind is 3,625. By the way, technically, we don't call this 13. Technically, we should call that 13. Because it's not 13. It's actually 18, right, in base 16. But most people that's dealt with it, they'll use the decimal names for these things and everything. This is where we get into problems, though, is this is a hexadecimal number, but all these are legal in base 10. You want to see it as a what? You want to see it as a base 10 number. And it's not, guys. This is 16 to the 0. This is 16 to the first. This is 16 squared, and this is 16 cubed. Now look at your powers of 16 on that thing. What's 16 cubed? 4,096. So that would be 3 times 4,096, right? You understand? What's 16 squared? 256, 16, and this would be 1. So this number is big. To us, it looks small. This is another advantage of base 16. We can represent bigger numbers with less digits. So base 16 has a better resolution than base 10. Decimal. Because what we're doing is we're taking the powers and coming up and getting, it's just that what you have to remember, if you see this, then you're going to have to get that to decimal too, right? You understand? So 3b, this would be 1, this would be 16. Well, this, if I was going to do this in positional rotation and try to get it into base 10, then you would have to do everything in base 10. Everybody understand? But that's okay, guys. I mean, we're not going from hexadecimal. We're not going to use hexadecimal to go between decimal. If I was going to go from decimal to hexadecimal, I'd use a calculator. Even me. right? Because it's so complicated. I'd have to use the division method. I can't use the subtraction method. I'd have to use that division method. And then I'd have to remember, if I come up and if I take this and this and I get 11, what I do over here is I'd write a B over there. If I get 11.65, then I got to take 6.5 and multiply it by 16 to get my whole number remainder, right? So it's a lot more complicated, but it still works. So we're not learning hexadecimal to know how to go between decimal and hexadecimal and from hexadecimal to decimal. We're not learning that. All we need to know is go between hexadecimal and binary, binary and hexadecimal. Because the only reason we use hexadecimal in computers is so I can give you large binary numbers with very little mistakes. And the computer does it all the time. PLC will do that. So when I get into logic later on, if you take advanced PLCs, and I want to AND this big binary number with this big binary number, I'm not going to enter that binary number. I'm going to enter it in hexadecimal. Right? You understand? Because it's what? It's a lot easier for me to enter. So these bases, hexadecimal, will come into a lot more play in the second term of this class than the first term. But they go ahead and get that out of the way. Any questions? Everybody okay? So all you got to do is just memorize what? Those 16 patterns. And you can see me, I can go through them. I can almost see the binary number without doing it, without going between, because I've been dealing with this what for so long. So let's look at octal. We need to learn octal because that's a base that's available in PLCs. You won't find octal on this computer anywhere. The PLC still use octal, or makes it available to programmers because it was the first higher level numbering system that they used. So here we're going to come up here. We have, so octal, we got numbers between 1, 2, 3, 4, 5, 6, 7. That's it. If I was to keep counting, I'd go 1, 0. Now I'm going to come over here, instead of using 4 binary bits, I'm going to use 3. And notice we run out of combinations. So each digit of octal has only 8 combinations. 3 bits of binary has 8 combinations. They work out to be exactly the same, right? You understand that? So I couldn't go between like a base 37 and go to binary because it don't match out, right? So what I would do is that if I had a large binary number, what I would do if I was going to go to octal is, instead of using groups of 4, I would use what? I use groups of 3. Always starting from the least significant bit. We can't start up there. I can add zeros over here to the left to get the right pattern and not change the weight of the number. I can't add zeros to the right, right? You understand? It's just like if I wrote a decimal number, you know, I could come over here all day and stick zeros over here. That has no weight of the number. If I come over here and start screwing around with that on the right-hand side, I change the weight of the number. So when you do these, you're going to start from groups of 3s. You can't start anyway. You're going to always start at the least significant bit and work toward the most. Everybody okay? And then if I need to get a 3-bit pattern, if I can't see it in my head, I can put more zeros down on the left-hand side. I can't put them on the right-hand side. So this would be a what? Anybody got it?
1, 3, 2, 7, 2, 5.
1, 3, 2, 7, 2, 5. And then I'm gonna make sure I put a base 8 down there, because that would be legal in base 10. That arrangement would be legal in 3 different bases. That's a legal number in decimal. That's a legal number in octal. That's a legal number in hexadecimal. So I make sure that I subscript it to make sure you know what base I'm doing. So octal, we split our binary number into groups of 3. Hexadecimal, we split our binary number up into groups of 4, starting at the least significant bit, right? You understand? So how would I go from octal, 3, 5? If I come up here and did that, that can't be octal. Why? Because octal only goes up to 7. Right, good. I've been known to do that. So this is base 8. How would I go here? I would just use groups of what? 3. I'd write down a 3. I'd write down a 5. I'd write down a 4. And then and if you converted those guys to decimal, they're going to give you exact same answer because those are equal to each other. So octal we use groups of 3. Hexadecimal we use groups of 4. So everybody okay on octal? So we're not going to go from decimal to octal. We're not going to go from octal to decimal. We're going to use octal to go between what? Binary or vice versa. And the book don't even teach you how to do that, but you could do the same method that we learned on binary. Okay. Everybody okay so far? Okay, now this is extremely important to understand how we use these terms. So we already learned what a bit is, right? You understand? I don't think this is in the book, but we're going to talk about this all the time. We know what a bit is. What is a bit? It's a single binary digit. And then we have groups of 4s. What do we call groups of 4s? I always thought the guy that came up with this had to be hungry. Yeah. When he did it. What do we call groups of 4s? We call it a nibble. And it's not any group of 4. You always got to start from the least significant bit, right? You understand that? Then we have groups of 8s, which we've lost. Memory is laid out in bytes, by the way. So if you say I've got 8 gigs of memory, you've got 8 gigabytes worth of memory. So memory in a computer is laid out in groups of 8s. And I hate that term gigs. I hate that with a passion. It's gigabytes. But that's okay. Then we have what we call a word. What's a word? 16. This is Allen Bradley. Allen Bradley. Siemens used bytes. Siemens splits things up in bytes. Allen Bradley splits things up in words. And then so that's pretty good. 16 bits. That's 65,536 different combinations. We could represent a number up to 65,535. We could represent numbers, sign numbers from a minus 32,768 negative to minus 376,568 negative. Did I say it right? One less positive. Then we get into what we call a double word. Some processors, some PLCs call this a long word. 32 bits, guys. This is the way I learned it because this is the way Microsoft talks about these corporate words. They call them quad words. Most of your PLCs call this a double long word. 64 bits. So with Allen Bradley PLC, we're going to be dealing with words a lot. And later on, if you take the PLC 3 class, we're going to move to the Siemens. Siemens likes to divide it into bytes because it manages the memory a little bit. So we okay here? Any questions there? These are terms you need to learn. Huh? Yeah, they lost, yeah, this one should have been a chomp. But they gave up right there. They wasn't hungry anymore. After they took their fifth and nickel in their bite, they weren't hungry. Still got these copied down? 'Cause I don't think this is in the book. Huh? This PowerPoint should be, I think I updated the PowerPoint. I think it's up on Blackboard. So all the PowerPoints in the class are up in Blackboard.
Why does it all the different things to be in all phase 2, 512,
Because they run in power. Every bit we add on the address bus adds a power of 2. So every time you go up, now normally what they do is they for some reason they've been going in groups of values. As far as your address in the data bus, they've been going in groups of values. But every time even if we add one bit, we double every time, right? You understand? So binary doubles. It goes in 2, right? 1, once we get past that 1 bit, 1, 2, 4, 8, 16, 32, 64, 128, 56. So that's why it does that. We got it? Everybody okay? You okay, Charles? So we went through hexadecimal, express system continued. We did that. This is counting in hex, by the way. Octal, we looked at that. Not very complicated. Now, what is a code? You got to understand, when I look at my keyboard, I have more than zeros and ones up there. So they got to have a way of representing not only numbers. We've looked at numbers so far, but a computer's got to have the ability to represent letters and symbols and all different kind of things, right? You understand? So this is where we come up with codes. So a code is when we're coming up here using a binary pattern. So I could come up here and I could go on the internet. So when I tap on a key, what my computer does, it sends a code, and then the program that's processing that information knows that code represents a certain key, right? You understand? We call them key scan codes. So we can look up key scan codes here if you're interested. And what base are they going to give them to? Probably hex. Some of them gives it to you in decimal, which I don't like. Oh, I can't see that. It's too small. Let's go to images. And here's the keyboard. Y'all can't hardly see it. But this is keyboard. One of them shifted, one of them unshifted. But it's C6C, 4C, 3B, 3A, 27, 22. So every time you hit on the key, then this is the binary code that comes from the computer keyboard into the application. And it's a code. So this is why I can play a video game and I can hit buttons. I can make F fly in a plane. F can mean lower the flaps. In Microsoft Office, this code would be an F, right? You understand? It would display that pattern. If I was flying an airplane, that code could tell my application to do what? To lower my flaps, right? You understand? Or anything like that. These are just codes. What depends on this code will depend on what application that's running in your computer at the time when it asks for information from the keyboard. So this code comes into that application. That application says, well, this key means this, right? You understand that? So this is the key scan code right here. Numeric key scan code. Now this is, I don't know if Apple's used the same key scan code. I'm pretty sure this is for the IBM compatibles, or what we call, I don't know, but they've got a code, right? If you got an Apple computer, when you hit a key on a keyboard, it gives you a code, right? You understand? Usually only 8 bits. With 8 bits, we can have 256 characters on our keyboard. Right now, I think we're doing what, with 122 or something like that. So yeah, these are just 8-bit codes or bytes. PLCs, most PLCs to send text information, they use a code. What's the first code they talk about in the textbook? That's what we need to do. Well, no, binary coded decimal. This gets people screwed up. So we have a code where we can directly represent decimal numbers. But it is not a weighted numbering system. It is a code, right? But I can guarantee somebody in this class is going to go directly from decimal to, and they're going to say it's binary by using groups of 4. With a group of 4, now these are the codes. For a 0, I use this. For a 1, I use that. For a 2, I use that. For a 3, I use that. For a 4, I use that. For a 5, I use that. 6, 7, 8, 9. I've thrown away 6 of my combinations for BCD. Because we get 16 combinations with 4 bits of binary. This is not a numbering system. This is a code. If I go between decimal and hexadecimal, I have to go through binary. I have to go through binary, right? You understand? So what we do with this code is, this is the code. So if I had a decimal number, not a hexadecimal number, if I had a decimal number like this, 3,645, then I would come up here, and some people call it the 1248 code. I would write it down like this. You cannot drop any leading zeros, by the way, because that's part of the code. Oops. And you got to write the code right. Oh, that was right, guys. So this would be BCD. This is not weight. This does not go 1, 2, 4, 8, 16, 32, 64. This goes 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. It is not a weighted number system. If I was to take this binary number and convert it back into decimal, if I use it, it's not going to come up and give you 3,645. It is not a number. It is a code, right? But it's so simple that it's very easy. So here's our patterns. It's the same patterns that I have to learn for hexadecimal, except it stops at what? 9. It don't go A, B, C, D, E, F. We throw those combinations away. This is called BCD. It's been around for years. In digital, we have counters that count in this. It's been around so long. Now, how they do that is really neat. But we have BCD counters. We got decoders that takes a BCD number and displays what we call a 7-segment display. I know what a 7-segment display is. It's these things that look like this. And they're usually light emitting diodes. Still very popular. And all you got to do is display numbers. So if you count the segments, we call it what? 7-segment display. We got, huh? Well, it could be LCD. It could be plasma display. It could be neon displays. The first ones that we had use this was actually neon gas. They looked like a vacuum tube, and they displayed the digits. They were really cool. Could be LED, could be LCD. I mean, if I look at a calculator, it's LCD, but it's still a 7-segment display, right? You understand that? We can display all the numbers of this. We got decoders that I can put a BCD number on it, and it will actually turn on the right segments to actually display the number. Like 9. 74147, 7447, 7448. Those are actually decoder chips. I'll bring one in here that's made up of LEDs. It's got about 10 LEDs per segment. But we have decoders that will decode this for us. But this is not a weighted number. It is a what? Code. I guarantee somebody in this class, I'm gonna say convert this decimal number over to binary, and you're gonna go to BCD. Somebody in this class is gonna do that. Please make me wrong. This is not. You cannot go between BCD. You cannot go from decimal to binary by writing these 4-bit patterns down. You cannot do it and get it right. Like I said, sure I can. Watch me. Binary coded decimal. Okay there. So we use 4-bit patterns to represent the digits of a base 10 number. So what would 5, 8, 9, 5, what would that be in BCD? Can't drop zeros because it's part of the code, right? You understand? It'd be 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1.
Oh, this sheet.
I don't know. I don't have the sheet. I think I got decimal then.
This is the chart that has hexadecimal, but then has decimal, it's about 5 to 15. But I think it's trying to show.
I don't think I don't have BCD on that chart at all. There's no BCD out there.
This doesn't convert if you try to just do the number.
What do you mean? This is not the BCD. This is decimal. This is decimal. There is no BCD on this chart. This is what hexadecimal represents in decimal. So an F in hexadecimal equals to 15 in this number.
Well, I noticed the first 9 were the same.
They are, but there's no BCD. You're right. The first 9 are the same, but there's no BCD on this chart. And that's what I was telling y'all. The first 10 combinations of the hex chart would be the BCD, but you stop at 9, right? You understand? And you throw away those other ones. It is not a weighted number system. It's a code. Yeah, I see what you're talking about, but that's not BC. You don't want to put BCD up at the top because it's only BC down through what? Down through 9, yeah. So we throw away 11, 12, 13, 14, and 15. So in hex, this would be a 15. This would equal to a decimal 15. In BCD, this would be 15. If I took this one and converted it to decimal, this would be 15. If I took this one and tried to do that 1, 2, 4, 8, 16, it's not going to come back and give me. So this is BCD. This is binary to decimal. This is BCD, right? You understand? But somebody, huh? But this is a code. Binary is not a code. Binary is a numbering system. Hexadecimal is not a code, even though I've seen people call hexadecimal codes. It's not. It's a numbering system, right?
When BCD is like displayed, would it show that there's like space in between the boards or something?
What we're supposed to do when we do BCD is we're supposed to write it down like this.
0, 0, 0.
We're supposed to put this, so in BCD, we're supposed to put this space right when you write the number. You're supposed to.
I mean, but that should help, like.
And it would help. But still, we're gonna have somebody in this class do that. I'm gonna say convert this number right here to binary, and somebody's gonna write down BCD. I guarantee. A class this size, I have never taught a class where somebody didn't do that. Yeah, that's what you would do. If you wanted to go to you'd have to go through binary, right? You understand? You have to do the subtraction or the division thing. BCD is not a numbering system. It's a code to convert a number from any numbering system besides decimal to BCD. The number must first be converted to decimal, right? You understand that? Because the only thing you can go directly from BCD is from decimal to BCD. You cannot go from decimal to binary just by using it. Then represent each decimal digit with a 4-bit BCD code. What's nice about these codes, they're really easy to keep up with. Now, another code we have is referred to as gray code. We have what we call closed loop systems. Automation depends on what closed loop systems are. Basically, what way a closed loop system works is the controller tells the device to do something, and then it sees if it does it. And we call this feedback. So the guy's got some type of sensor out there. I tell it to do this, and then the sensor comes back and says, "This is what I'm doing." You run into this. Anybody got a speed control in their car? That's a closed loop system. So somewhere there's a sensor out there that senses the speed, the actual speed of the car. So when you engage that thing, you say, "This is my set point." And then you get feedback saying, "Okay, this is how fast you're going. If you're going too slow, what does it say? Speed up. If you're going too fast, what does it say? Go back." So this is a sensor. One of the things that we use to actually sense position is something called an optical or encoder. The problem is that anytime we count in binary, so if I was going to count in binary, the problem is when I count in binary is that in electronic circuits, we have what we call propagation. This is how long it takes to propagate through something. So if I was using 4 bits, that would be equal to a 0, right? And this right here would be equal to a 1. How many bits changed? 1. Here I come over here, I got a 2. How many bits changed? 2. Okay, right? Then I come over here, I have a 3. How many bits change? I come over here and have a 4. How many bits change? 3, right? You see that? Then I come over here and have a 5. So what would happen is the more I add, this would take longer to get this count than it would to this count, because here 3 bits had to change, right? You understand? And the problem is if I go backwards, we have the same problem. So sometimes 3 bits have to change, sometimes 4. We're only dealing with 4-bit binary numbers. So what they did is they came up with a counting code. This is a code. It's not a 1, 2, 4, 8. It has nothing to do with it. This is just a pattern. This guy here's out here spinning, he's throwing these numbers out at me, right? Y'all see that? This is not gray code, by the way, that's binary. So gray code, this is gray code right here. This is a section of gray code. I don't know this. If I dealt with it all the time, normally what we do when we have these complicated codes is we look them up in a chart. So if I was going to count in gray code, this would be equal to a 0, this would be a 1, this would be a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, I'm going to stop right there. But let's go between the code for a 0 and the code for a 1. So far it looks kind of like binary. How many bits change between a 0 and a 1? Okay, then I come to the code for a 2. How many bits change between a code for a 1 and a code for a 2? 1. Then I go from a 2 to a code for a 3. How many bits change between the code for a 2 and the code for a 3? 1. Here I'm going from a 3 to a 4, the code for a 4. How many bits change? 1. Here I'm going from a code to a 5, how many bits change? 1. What if I go from a 5 to a 4, how many bits change? 1. So no matter how fast we count, between each count, we only have how many bits change at any one time? Just 1. Whether I'm counting up or I'm counting down. Now I can design a system where I don't have to say, okay, this time I gotta wait for 4 bits to change, this time I gotta wait 2 bits to change, right? You understand? This makes it very, very easy for a counter to count. So these are called gray codes. We can't do math with this. We can't do the 1, 2, 4, 8. If I wanted to figure out what a 6 was, I would do what? I would look it up in the chart. Now, if I dealt with gray code, that was my job, then odds are I could do this, right? So gray code is a counting code. And what advantage of gray code is no matter whether you're counting up or you're counting down, how many bits change per count. Yeah. So we have gray code encoders out there. Now they have to be converted, but once we get it inside the computer, we can really. Here's gray code. They're counting in binary. This is. I don't think this is. Yes. Then we get into alphanumeric codes, and this is where the book kind of gets into a little problem. The first code that I ran into to represent text was called the American Standard Code for Information Interchange. And this is a true acronym. An acronym is when you take a phrase and you use the first letter off of each phrase. You see them, they'll drop 4. They'll drop 4s and E's a lot to create another word. So we call this ASCII. So ASCII is an acronym. And computers, anything we do is an acronym. We'll take a phrase, we'll say IDE, which stands for Integrated Drive Electronics, but we just say IDE and we call it an acronym. But technically it's not an acronym because it didn't form a what? Another word. American Standard Code for Information Interchange. It was originally a 7-bit code. By the way, you can tell the number of combinations available by taking the base and raising it to the number of digits. So a 7-bit code, that would be 2 to the 7th, which would give you 128 different combinations. So we can represent 128 different characters can be represented. Data is often sent in bytes or groups of 8s. So what they did is originally our transmitting of data was very poor. In fact, when memory for computers first came out, they had a problem with bits inside the memory changing. So what they wanted to do, they wanted to come up with a real fast method where they could check to see if the information being received was the information transmitted. So the first method they used, which is still used by the way, is one referred to as parity. And we have 2 types of parity. We have what we call odd and we have what we call even. And what I would do is I would come up here and I would take a 7-bit code. Okay. And what do y'all want to do? Do y'all want to use odd parity or even parity? Okay, even parity. So what the transmitting said, so the transmitter would come up here and all it's dealing with is this guy right here. This was the parity bit. And what it would do is it would count the number of ones. How many ones do I have? 1, 2, 3. Is that even or odd? So what do I need to do with this bit right here to make it even? I'll put a 1 up there. And then this would be transmitted. The receiver, what it would do, it would come up here and it would count the number of ones. If it came up with an even number, it says it's okay. If it came up with an odd number, it would say it's not okay. Right? Does that make sense? Now, but you had your transmitter and your receiver both had to be set up exactly the same. And y'all see this. Some of our PLCs use the old RS-232 port, and you'll see it's got parity up there. So that's why it was an 8-bit code. So Parity couldn't find an even number of bit changes, but it could find an odd number. So it was about 95% accurate. I can't deal with 95% accurate inside my computer. Of course, memory has evolved, and it's very, very reliable now. So now we use something we call CRC codes. So this is the old ASCII chart, 7-bit ASCII. It has 7 columns and it has 8 rows. Oh, I'm sorry, it has 7 columns and 16 rows. And the ASCII code is a binary code, but it's usually given in hex, so we can make it real easy for me to put it in a chart, right? You understand? Everybody okay? So these first columns, these are control codes. Null, start of header, start of text, enter text, enter transmission, inquiry. These were 2 that we use a lot. So if I was using parity and I received the data and I had wrong parity, then what the receiver would send back, it would send back a not acknowledged, a NAC. And that would tell the transmitter to retransmit the data. This is what we call a software handshake, where every time the guy receives it, if it received it, it would send back an acknowledge, right? You understand? If it got the wrong data, it would send back what? Not enough. Or NAC. Acknowledge, ring the bell, backstage, horizontal tab, line T, vertical tab, form T, character turn. I have no idea what that's for. These are just device control codes that were used by different things. Dot acknowledge. Then I've got all. So these are all what? These are what we call control codes. These codes right here, this is so a 20, which would be this code right here. And you run into this a lot if you're into HTML. So this would be the actual code. And what would that tell my computer to do? Tell me to do a what? Yeah, space, right? This would be an exclamation mark. So 26 base 16, 26. So the way you would do this, of course, is you would split it up, right? This is the most significant digit. This is the least significant digit. So an uppercase R, what would be the ASCII code for an uppercase R? I gotta go back and turn that off. Somehow I got it enabled. So this would actually be the code 5, 2, right? But that would actually be the code. But the chart is laid up in hexadecimal, so you can do that, right? So you can say 5, 2, right? You understand that? So what would be the code for my name? I need an uppercase R. What would that be? 52. I need a lowercase I. What would the lowercase I be? Yeah, lowercase 69. And what would be the lowercase c? 63. What would be a lowercase h? Everybody okay? So the original display worked off ASCII, by the way. What was the uppercase R? What's that? 5, 2. Now look at the M up there. Now this was where we put attribute codes in. I'd have to go back and look those up. We'll just make something up. Can you see it change? What would be the code for lowercase I? We enter next, by the way. What's that? 69. Won't be the ASCII code for lowercase c. What's that? Lowercase h. Is that? By the way, 20, these are spaces because I'm working on that line up there. Notice this is nothing but spaces. So notice 20, I'm changing them over. So what I'm doing is I'm storing information directly into the address for the video movement. Now, this is not graphics, this is text. We're doing it in text mode. So what did I have to know? Well, I had to know that I'm entering all this information in hexadecimal, even though the computer, and I'm using what code chart? I'm using the ASCII. So originally the display on the computer worked off nothing but ASCII. There was none of this graphics, these pixels. All right. Yep. So the book talks about EPSODEC. I've never seen a PLC use EPSODEC. This was a code that was originally set up by IBM's been in the computer business for years. And so the first code that they used was a code called EPSODEC. And that's an acronym for what? They say that it's, here's EPSODEC. Let me find it. Here's EPSODEC. Yeah, so here, an uppercase R would be equal to, okay, right here, would equal to C9, right? Oh, I'm sorry, D9. So this is EPSODEC. I've never seen a PLC use EPSODEC. I don't know why the book's even brought it up. They said it's enhanced ASCII. It is not enhanced ASCII. So if the book says that EPSODEC is also called enhanced ASCII, the book is wrong. What they did on enhanced ASCII is they dropped off the parity bit because memory had got a lot better, which gave them 256 combinations. This is enhanced ASCII. So notice what did they do? They added a lot of Greek symbols. They added a lot of graphic symbols. So this is enhanced ASCII. So it's actually the other 126 combinations we get when we added the 8-bit. By the way, I don't have a numeric keypad. But if you're running with a Microsoft Office or Microsoft Word or PowerPoint and you want to get one of these weird characters, all you have to do is hit the Alt key and enter the decimal, not the hex, because it's translating from decimal and binary. And you hit the Alt key and type in these decimal numbers right here, and that image will pop up on your document. We use it a lot. We use this symbol right here a lot. 334, this is the symbol for Omega. A lot of people will go in and they'll bring on their symbol chart, they'll find the Omega in there, and then they'll type it. All I hit is all 334 and it pops up there. We use this guy a lot, we use micro a lot, 330, we use degrees a lot, 160. Right here, 167. I use that a lot. So y'all know what I'm talking about, the symbols, right? You can do it in Microsoft Office. You could hit Alt 41. You could hit Alt 65, which is, the A would pop up there, and you wouldn't have to hit the A key, but that would be hard. I can't do it on my keyboard because you got to do it from your, numeric keypad. Because the codes are different. If you look at the code for a 1 from the numeric keypad and the code for a 1 on the numeric keypad across the top, they're different. So if you're gonna do these, you have to have and my computer don't have a numeric keypad on it. So the book says that EBCDEC is also known as Enhanced ASCII. No, it's not. It's known as EBCDEC. The other one we're going to look at is something called Unicode. Unicode. The problem with ASCII, even with 8-bit ASCII, we get 256 combinations. Originally, when the internet came out, guys, it was ASCII. So that means every web page was in nothing but English. If you lived in another country, well, that's it. You had to learn English to use the internet because everything, all the text that pops up on the screen is still basically in ASCII over here. But what they realize is that we need to make the internet is supposed to be international, right? You understand? So what did they do? Well, they came up with another code. Predominantly, it's a 16-bit code, 65,536 combinations. We have what they call Unicode. We have what they call UTF, which is enhanced ASCII. That's all that is. So it's an 8-bit code. Then we have what we call the UTF-16, which is a 16-bit code. And so if I'm over here on Microsoft Word and I see something on here that's not in my keypad and I want to enter it in there, then I can come over here and I can go to insert, and then over here I can go to symbols. And now if I look right down here, it says it's a character code. And what code is it? It's Unicode, right? You understand? Now the first ones, if I was to look up the code for an A on the ASCII code chart, it's 41. So the lower 28-bit, the lower 256 combinations is enhanced ASCII. That's all it is. Once I get above those combinations, but look what we can do, guys. Now, right? Because now I got 65,536 different combinations to deal with. There's actually a 32-bit, but I've never seen it used. And these are the character sets that's usually installed with Microsoft Office. Have y'all ever been to a website and it wants you to download a character set? Well, all you're doing is just adding those codes to the codes that's in there when you install Word on your computer. So I don't know if y'all have ever been to a website that says you need to download the Korean character set. I've been there. Of course, I don't speak Korean. So Unicode, this is what we got now. This is a Microsoft Office uses it. By the way, if you know the codes, so let's do something. Let's find one of these big codes, like this right here, not equal. And what's the code? 226. PowerPoint don't like it, but Microsoft Word does. I can say 226. What is it? 226? It's what? And then you can hit Alt X. Alt X, and then it'll pop the code in there. I don't like to do it on PowerPoint, but it works great. So if I knew the code, I could do that on my keyboard, right? For I think this is about it, guys. Let's look and see. So this is the 8-bit. They did come in and get rid of all the control codes, so we got all the little most time. And then that's the glossary. That's it, guys.
Now, they have codes for emojis probably now.
No, I don't know the code for emoji. I know it is, I know it's a
Add
code.
them probably.
Yeah, we don't use emojis much in Microsoft Office.
Oh, yeah.
We do it a lot on our phone, but it downloads those codes for you. You know, they say you can update your emojis. You know, but you know it's a binary code, and somewhere all the codes for a smiley face for the iPhone has got to be the same. And that's all they're doing is they're sending you a code, and it picks that graphics pattern out of memory somewhere. So what's the next chapter? We were coming back from Cleveland and we pulled into an Applebee's and we had no idea where we was at. And I walked in and I asked the waitress, I said, "Where are we at?" And you know what she said? Applebee's. I said, "No, I mean, where are we at?" So I thought, what's the title of the next chapter?
Oh, you put out wood devices.
Okay, so we're fixing to get into the POC. Thank you, we needed a laugh. We're gonna have to kind of, y'all listen up here. There's a lab on number system. The problem is that everybody don't have a lab book. But what I'll do is I'll contact the bookstore tomorrow, and if we don't have the lab book, then what I'll do is I'll copy it out for the people that don't have it until they get it, and then we'll make these due Monday, okay? Have a good Wednesday. Yeah, Monday's a holiday.
That's weird.
Well,
We got started school and going
that's good class. Ours will be after that. It's on the calendar.
Yeah, I thought so. So why are we up here instead of down there?
Now where?
Near in the room where all that stuff is.
Because you can't teach your class.
Why not?
Have you been in 200? It's a bunch of lab things.
Oh, I haven't been in 200 yet.
200 is the field.
Oh yeah, they're doing there's a whole bunch of
That's
stuff.
where we go in there and take tests.
Yeah, the automotive stuff's all being moved around now, isn't it?
No, it's not. No, we're gonna, our labs are here, down 8200.
What's going on with the automotive stuff? Remember how she was saying that getting all that area down there for the robotics and stuff?
Yeah, I don't know. The guy doesn't give up. The guy that's over our own program. Give up his study. They were rebuilding building C. They redid it for the automotive program.
Yeah. Oh,
I enjoy this stuff. Coming back to that. It's so long.
Luckily, I can say that. Fine. Somebody doing